Hello, hello everyone, and welcome to the DVCon Europe 2020. This is a panel session. Move the next slide, please, Hannah. So this is a panel session, and today, so I am Tran Nguyen. I am the panel chair of DVCon Europe 2020, and I am very excited today to open the session about the panel of verification challenge of an Exascale supercomputer. So we have a lot of experts around the table today, and we will introduce them shortly. So before this, I would like to give some background of this session about the questions that if you want to ask during the display of these sessions. Can you move to the slide? So as you know, this panel is a pre-recorded sessions, but during the play, you can ask any question using the chat features. And if any panelist is online, he can answer the questions. Otherwise, it will be posted within the conference, and you can post any further question that we will answer later on, anytime by the panelists. So let's start the panel now. So I'm very happy to introduce you our moderator, Jean-Marie Brunet. So Jean-Marie is the Senior Director, Marketing Director for the Emulation Division at Mentor, a Siemens Business. He has served for over 20 years in application engineering, marketing, and management role in the EDA industry, and he had IC design and design management position at ST Microelectronics, Cadence, and Microns, among others. Jean-Marie holds a master's degree in electrical engineering from ISEN, Electronic Engineering School in Lille, France. So now I let you, Jean-Marie, to introduce the panelists and to start the discussion.
Thank you, Tran. Thank you. Looking at the picture of myself reminded me when we used to go to the office every day and shave and wear a tie. So this is, those times are really behind us. So thanks everybody for joining the panel today. We're gonna go through alphabetic order at the beginning here to introduce the panelists. So I'm gonna ask each of you to provide a brief description of yourself, your role, and where your company fits into the structure of the Exascale computing situation and challenge. So we'll start with Christian Beckmann from Atos.
Yeah, hello, I'm Christian Beckmann, and I'm responsible for all ASIC verification activities Atos is doing in France and with a team in Bangalore and India as well. I'm as well a work package leader for the European Processor Initiative, the EPI project, responsible for the top level integration and verification there. I joined Atos a little bit over a year ago, and prior to this I was doing design and pre-silicon verification for various companies, mostly in mobile, not in high performance computing. So I was working for Intel Mobile Communications as a manager and verification lead for several years, and prior to this with Infineon Technologies, all this in Sophia Antipolis in the south of France. Prior I was at Siemens and Infineon in Germany, in Düsseldorf, and I started there like 22 years ago as a designer of hardware. Okay, so talking about Atos, maybe. Atos is the only manufacturer of high performance computers in Europe. We built the whole systems, like the Sequana family. And in this, we develop our own ASICs in my group that are mostly like our interconnect, BXI or NIC and switches, partly in cooperation with others. These are most custom designs there. Not much standard IPs. And with this and the processors of other providers, we built the whole system. And in the European project, the EPI, we are contributing in this development of a European processor now.
Very good. Thank you. And I forgot to say, I'm based in Santa Clara, California. I'm recording from Santa Clara. Where are you recording from today, Christian?
I'm in Sofia Antipolis in France.
Very good. Thank you. Next is Roger Espasa from SemiDynamics.
Thank you very much, Jean-Marie. A few words about myself. I started with the Digital Equipment Corporation in their Alpha Processor division, then spent 14 years at Intel, where I work on Halem a little bit, and then on Larrabee and the Knights family, the Xeon Phi family. From there, I spent a couple years at Broadcom working on an out-of-board ARM core, and then 3 years at a startup called Esperanto Technologies, building a 7-nanometer machine learning accelerator. And now I'm the CEO of SemiDynamics, where we're building RISC-V cores. And those cores, we're proud participants of the European Processor Initiative. Those cores are going into the accelerator of the EPI. So, you know, our role in the Exascale world, we hope to provide European technology for Exascale, in particular on the accelerator side of the world. You know, today there's the CPU driving and there's an accelerator executing the heavy stuff. So our cores are going straight in there. So that's our role. We hope you check out our cores in our web. And I'm recording from Barcelona, Spain. Thank you.
Very good. Thank you. Next is Mark Glaser from Cerebras.
Thank you very much. My name is Mark Glasser, and I've been involved in verification for probably longer than I care to say, mostly in simulation-based verification, simulation and modeling. I've done that a number of places, working for a long time in the EDA industry, and then probably for the last 10 years or so in semiconductor side. My company, Cerebras, is building large-scale computers for the machine learning and artificial intelligence space. We build what we call a wafer scale engine, which is a single substrate of silicon that has, our current generation has 800,000 processors on it. And we're using that, as I said, for machine learning applications. And so that's kind of the scale of the problem that we're trying to solve here in terms of verification, as well as design. And I'm talking to you today from the lovely Santa Cruz Mountains in California.
Very good. Thank you. Good to see that your house didn't burn.
No, thank you. We're happy about that too.
Thank you. Next, we have Gajinder Panesar from actually Mentor now.
Hello. Yeah, I'm Gajinder Panesar. I've recently joined Mentor, a Siemens company. Previously to that, I was CTO at a company called Ultrasoc. I spent 5 years there, and then previous to that, I was a performance architect at NVIDIA. Before that, I spent about 11, 12 years at a startup called PicoChip, where I designed CPUs and interconnects and the programming model for a many core baseband system where we invented the femtocell. And then before that, I spent maybe 12 years at ST in MOS. So I started out in parallel processing a long time ago, and now I've graduated to providing silicon IP for complex systems. Mentor, as you know, will know very well, in the EDA space, but now with the combination of Siemens acquiring Mentor, the future is much greater. We'll be going from very small, low-level components to EDA, to emulation, to prototyping, to in-life for the whole spectrum of products out there. And I'm calling from Bristol in the UK.
Very good. Thank you, Gaj. Next is Nasr from SiFive.
Hello, my name is Nasr Ullah. I'm the Senior Director of Performance Architecture at SiFive, one of the founding RISC-V companies. And in the last 30 years, I have worked on performance analysis, modeling, and verification, performance verification, to the life cycle of microprocessor products, from both high-level C-based simulations to RTL, to emulation, all the way to silicon, the entire life cycle. It does involve performance and power analysis, but both the hardware and software levels. And I did all this for a plethora of companies, starting with Motorola. I worked for the first risk systems that Motorola did, that was in the Patriot missile and the US nuclear submarine, the 88,000. And from then on, I went into PowerPC, the Apple, Motorola, IBM PowerPC initiative, and worked through the full life cycle of all PowerPC processors that was used in the Apple Macintosh. And I worked with the Apple team there on that. And then on to Freescale, when this consortium broke up, where we did communication processors and SoCs that are used in Juniper and Cisco's routers and Alcatel-Lucent and Ericsson's base stations. And then ended up in Samsung before SiFive, where I worked on the Galaxy phones, chips for the Galaxy phone series, from the Galaxy S7 all the way to the S12. They've changed the naming convention towards the end before I joined SiFive. And in those roles, mostly performance, power analysis, architecture, and a plethora of all those things. I'm from Austin, Texas, and I joined SiFive to work on RISC-V earlier this year. And it has been a blast. And SiFive is very interested in Exascale computing and is working closely with the European Computing Initiative. They're with their partners, Barcelona Supercomputer Center, BCS in Spain. And BCS is actually using a simulation framework that SiFive uses to develop a full system model. They're using some of our simulation framework and with others, and we are working with them on enabling that. In addition to that, we are working with them on adding to the RISC-V standard for vector processing, because they want to have a lot of vector processing to make Exascale computing even more powerful. But we're not just doing it on the hardware side, but we're working with them on both hardware and software. We have the founding members of RISC-V, Krista Asanov, Yun-Supi Lee, and Andrew Waterman there, as well as the creator of LLVM, Chris Lattner, in SiFive. And we're working closely with BCS to make this a better place for the industry in general, the methodologies that are in place. We're in a unique position to do that. I guess that's it for me. Thank you.
Very good. Thank you, Nasr. Good to see you. And next we have Wesley Yan from SiPeral.
Okay. Hello, everyone. My name is Ying-Chih Yang. I work in SiPeral and the CTO of SiPeral. So before joining SiPeral this year, I worked in Atos, and before that, I worked in ST in Grenoble since 2015. Then even before that, I worked in Taiwan fabric design houses for 18 years. So I came to France in 2015. Then today, SiPeral is part of this EPI project, European Processor Initiative project. And we at SiPeral now working to build a high performance, low power microprocessor that is powerful enough in order to address the post-Exascale applications. So this design need to be scaled for Exascale and also post-Exascale together with the general purpose computing and also with the hardware accelerations that we have in the EPI project. So today the topic that is verification in Exascale computing, it matters us a lot.
And you are calling from Paris, correct?
Yes, that's correct. Thank you.
Very good. Lucky you. All right. I'm from there. So anyway, thanks everybody for a quick introduction about yourself and the company. So the title of the panel is Verification Challenges for an Exascale Supercomputer. So when I prepare for this, to moderate this panel, I start to think about how does it fit within what we do with supercomputer type of machine like Veloce, which is a billion gate design verification emulator. And I started to look at it from an angle of we also do supercomputer ourselves. And you have different way of approaching the realization of a very complex type of system like this. And you have a way which is looking at a very high level system architect, very top down to an implementation, but the system level drives much more the realization and therefore the verification challenge associated with how to verify that complex system. Or you can work directly from more bottom up all the way to the silicon, which is how we do it with Veloce, preparing our own silicon, which looks at all the attributes of what is necessary, and bottom up from the silicon to the system, the chassis, the operating system, and all those pieces to fit together. So I see clearly that from the architecture realization, but as well the verification of something that complex, there is potentially two ways of doing it. A bottom-up approach where you verify at the smallest level cluster possible, and you move up through the realization of your Exascale supercomputer, or you start from the top very architecturally to verify what's going on to go down. So I'm curious to see from all of you, and I'll go through alphabetic order as well, or if you want to interject and say something, please do so. What is your view? Is it bottom-up? Is it top-down, or it's a mixed mode? And we'll start in alphabetic order with Christian.
Yes. Okay. So we at Atos, we have to say we are still working bottom up, the classical approach for our interconnects and so on. Of course, there's all the definition on high level. It's a system engineering that defines what needs to be done to meet the targets. But yeah, the design is done in a bottom-up approach, and we see the deviation we get when we develop hardware and software more or less independent. Yeah? They have some shared requirements, but yeah, we saw that then the software is not matching the hardware, or not using the hardware like it was intended. So we are planning, and we are fighting to get this done now, yeah, to use a more top-down approach in the future.
All right, very good, thank you. Roger, what is your view on this, please?
Well, we are also going bottom up. I want to say that I think in Exascale, strictly speaking, top down is not going to be possible for anyone, in the sense that Exascale is hundreds of thousands of compute units, be them actually a mixture of CPUs, GPUs, interconnect, and that's outside the reach of anyone to validate before you build, I think. So you'll never be in validation at the scale of the thing you're offering to build, in my opinion. So I would say that we're bottom up, or maybe medium down. And by medium, I mean we're interested in at least being able to verify a significant section of that exascale thing. Maybe think of a rack. Especially for if you're going for a chiplet strategy where you have multiple chiplets talking to each other on a board, and then those boards form 1U and 2U servers, and then that forms a rack. What I think we need from the validation community, people providing billion gate emulation, is not so much a large system. We need lots of cheaper small systems connected, or in an easy way to connect with the SerDes or the protocols that the real thing is going to use. So I think there's still plenty of business for all of you building those kind of logic emulators. But from my point of view, the business is not, oh, we can offer you now 20 billion gates, 30 billion gates. That's not what we need. We can offer you lots of little boxes, and we offer you the flexibility to connect them the way your system is going to be. That's my way. I don't know if that's bottom up or top down. It's, but at least it's, I would call it a cluster view. I want to connect multiple things that are part of that final exascale system.
It's a good point. We see that as well a lot with machine learning AI type of designs, where most of the time they need to start at the smallest cluster level possible to verify the functionality. Then after that, it's a game of scaling. They need to assemble very quickly multiple clusters. So it seems to be very related to what you are saying as well, with machine learning and AI. Thank you. Mark?
I don't think it's a matter of either or. I think you need to look at the system both from a top-down perspective as well as from a bottom-up perspective. You know, so from the top down, you need to be able to look at you know, the entire system, the total performance, throughput, and so on. And then from bottom up, it's kind of a traditional verification problem where you need to break things into small pieces and verify them independently, and then hook them together in larger pieces and verify those subsystems and so on. So I don't, you know, like I said, I think both top down and bottom up are required. I don't think in that respect is very different than more traditional SOC style verification. The fundamental difference really is the overall scale of the problem. So you just have a lot more to do.
So I agree with what you say, and this is something I forgot to ask previously. If you could comment on what is the capacity challenge you're dealing with. I mean, maybe the small and the smallest cluster is relatively small, but when you have to assemble an exascale supercomputer, what capacity are you talking about? Are you talking about 10, 20, 30, 40, 50 billion gates? And yet, so
well, our current generation, the device that's in the field has 1.2 trillion transistors on it. So we're not able to simulate that all at once.
okay.
I don't think anybody can. We would need a computer bigger than that to be able to simulate that many transistors or even that many logic gates.
You could emulate that type.
I don't know that we could emulate 1.2 trillion transistors worth of.
Well, that will, you know, in billion gates, that will be what, 200? You know,
it would be a lot. But the way our the architecture of our device is very regular. So there's lots of small pieces that are similar, and they're constructed in blocks. So we can verify those blocks independently, and then we can put them in groups, however many we can fit on our compute servers. You know, so it might be hundreds that we can fit all at the same time, but not necessarily thousands or tens of thousands, certainly not hundreds of thousands. And so we have to kind of do some extrapolation from the small to the large, because it's not really physically possible to simulate or emulate even the entire device.
Okay, thanks. Sorry, Roger and Christian, I forgot to ask you, what's your capacity challenges? Can you give us a sense? Is it trillion gates, trillion transistor as well?
Well, it's the same scale problem that Mark was alluding to. The actual chiplet that's going to be at the heart of the accelerator may not be that big, and certainly today's capacitors are enough. The problem is you want to gang together thousands and thousands of those, and that's exactly the, you know, Mark is doing it on a wafer, we're doing it on boards, right? But it's the same problem. It's combining together, and so we have to extrapolate the same way. It's you gang together a few of those, learn from that, and then try to extrapolate your way up, and you'll never assemble the whole thing before you sell it. Or I don't think anyone really would try to do that. Okay, thanks.
Yeah, I agree to Roger that yeah, I think the machines are large enough to have the single chips on in one emulator. Yeah. But then we need to create larger, to scale it, go from 64 nodes to 32,000 nodes. How can this happen there? It would be interesting to have these multiple tiny signal systems we can plug in together, so we can match the challenge of the heterogeneous systems, that we have always CPUs and GPUs and those from different vendors, so we could really make them all talk together, and that would really help.
Okay, thanks. Next is Gaj.
Right, I have a similar view to Mark's, except I'm going to be a little more extreme. I think it should be top down, and one of the reasons why we suffer so badly with verification and validation is because we don't have a coherent programming paradigm. Because if you have a coherent programming paradigm, then you can then go bottom up to implement that paradigm and support it. What's happening? I mean, some new, some of the TensorFlow type things, the new systems coming out will help with that program paradigm. But generally what we find is that people put things together at the low level without an understanding of where it's going to go. So you're bolting in a bunch of CPUs and some interconnect, and then you get to a point where you put software in it and it doesn't appear to do what you wanted it to do. So I think it should be top down, and then you have bounds that you feed into the bottom where those bounds are met by the implementers of the microarchitectures. But trying to come up with a system that will support an ad hoc program paradigm is just always going to take a lot more effort, and you're never going to get the performance that you would want to get.
I think the problem that you're alluding to is the problem of trying to generate a realistic workload in a simulated environment, right?
That too, yeah. But that as well. But even if we had a complete simulated environment, then if you use conventional off-the-shelf components that you stitch together and you're trying to map on a particular programming paradigm, I think you're asking for trouble. If you start off with this is how it's supposed to work from a software view, and you implement the hardware accordingly, which would then satisfy those SLAs, for want of a better phrase, I think you were in better shape, and it would make your verification a lot easier.
Right. So again, one of the problems of these large-scale systems is trying to, you can simulate it at, let's call it unit level, for lack of a better term. You can simulate a unit level thing, and you can synthesize some sort of stimuli for it, but trying to extrapolate that into the entire system with hundreds of thousands of processors and developing a workload that you can simulate that would be somewhat realistic is a difficult problem, right? So the only way to really do that is to run the software, run the entire software stack, and that's essentially impossible to do. As we talked about a minute ago, right? Just the scale of it is beyond what we can do.
And that's one of the reasons why I think you can only do so much verification before you actually build your system, and then the rest has to be done while in situ. You need to be able to get enough visibility of the system in operation. That means not just the hardware, but the software in situ, to then, you can then retune your software or whatever to make it performant.
Yeah, so when you talk about consistent programming paradigm, what are you referring to exactly?
So rather than having clusters of standard CPUs with memory mapped accesses, you have particular coherent. So let's take one example, CSP. So if you had a CSP like a program paradigm, the hardware, once it satisfies those communication points, so compute-wise, they can do whatever they like, but at the point at which you transfer, it's always guaranteed to do it in those bounds that you lay out.
I see.
And introducing non-determinism will also affect the way your software and your system will perform.
Certainly.
Nasr, what's your view on this?
Well, I think all the other speakers touched on things on everything that I'm interested in what should be done. SiFive, develops processors, and as a standard semiconductor house, we work with a lot of partners to build the systems. And our partners build systems that go from, a few processors together to dozens, to hundreds, to thousands. So the key thing there is scalability, being able to have these building blocks that you can build up to, but that could be building blocks such that not only can you build up to getting much larger scalar systems, but the verification, if you're doing it at the low level, can somehow translate as we go bigger. And I agree with Gajinder about you have to do this in the real system. You cannot do this with simulation or emulation easily at the large scale system. But what I would say is, we build it bottom up, but we should design it top down. So I would say it should be a mixed mode approach. BCS, for instance, right now is looking at very high level simulation methodologies where we take very detailed models of the individual components and they're putting together in large system simulations to kind of get the idea of the design of what it should be. And then we are building it bottom up, but we have to make sure there is an intersection point. And that is the difficult piece because verification, performance, power are the intersection points. So sometimes what we do is, we know that there'll be thousands of processors in Exascale system. So maybe we design each of them with much more lower power so that when in the combination, we have an aggregate good power system. We have to think about things like that. But then there's a couple of other things to think about. The interconnection between all those building blocks, the memory subsystem, the memory bandwidths, the capacities, those, how do we check those? So one of the philosophies I have is when we develop these things, we have to put enough probes in them, whether it's performance or power monitors, instrumentation, so that when we build a big system and we have to do things when we do most of our testing when the big system is there, that we have the instrumentation to look and probe to understand why, to be able to debug things. So,
I think I think you highlighted it. It's not about the core, it's about the system. We need to have, the whole systems need to work. There's no point, we all know this, there's no point in having a really performant CPU and you stick it into something and then the periphery and the interconnect falls over. So we need to consider the whole system when we're designing it, not from the core level upwards.
Exactly.
Okay, thank you.
There's one more aspect, is somebody touched on workloads there. You're right, there's no real workload for us to use. There's lots of workloads, there's too many for Exascale systems, but how do we take that workload and then relate it all the way back to our basic building block? That's a very difficult
I will go back to the workload in a second with all of you guys, because I have some question on workload. How about the view from SiPeral?
Okay, so I think that previously you have described those topics very clearly, because I think that we are talking about performance and also functional verification. For sure, I believe that functional verification is always bottom up, because that in order to build such processor, especially the skill that we need to build high performance processor, you need to rely on rock solid component, and for all those to get in those rock solid component to be built up, you need to verify that bottom up. There's no way to do that top down directly. But on the other hand, that when we talk about Exascale, we are referring to a system performance. Then in this case, you do need to have the top down view in order to have a performance validation and verification way in terms of simulation, in terms of emulation, and actually to remap that, to associate that with the index you measure after you get the actual silicon. So there's a methodology we need to be linked together by this such kind of cross-checking between different index. So that's what I see here. So I would say that it's a different way we look at nowadays in application-wise, that application, how do we ensure the software can utilize and make best use of the performance of the we deliver in the chips. That is the challenge we have today, beyond the traditional functional verification we have. So I would say in SiPeral, in order to design such high-performance chips, that right now we are using bottom-up for verification for function, but top-down for performance validation.
Okay, very good. Thank you. So let's open now the discussion to how do you actually verify that the supercomputer you are assembling is behaving from a performance and power standpoint to the benchmark or the workload that you have in mind. For a traditional, single CPU, GPU, mobile, there is some very known benchmark that we are able to emulate that with hybrid type of functionality. We're able to see roughly all the way to booting and run the application, how the silicon is behaving. But that's a single piece of silicon. Here you're assembling multiple pieces, board level, many system talking to each other. How to verify that the workload that you run through your supercomputer system is behaving correctly, and you are providing the response in performance and power that you're expecting.
So can I I'll take this. So I think Nasr alluded to it, and we need instrumentation, and the same instrumentation, and this is what my previous company did, Ultrasoc, and that's why Mentor acquired us, and it's called embedded analytics, and we need those both at the emulation prototyping level and in situ, and you use all from design to implementation. Running the real workload is eventually going to happen in the field. It's not going to happen, as Mark said, it's not going to happen in your emulator or in your simulator. It's going to happen in the field. And so these embedded analytics that Mentor provides will give you that information, and then that feedback must come back to your design for future generations. So that's how I think it's going to work. The majority of the time spent in development is not chip verification. It's actually getting the whole system to work. And it's about 75% of software development is spent debugging and optimizing your software.
I see that's also the same thing of what we see in SiPeral, because that our potential customer, they are looking at different kind of workload, and we are trying to extrapolate and also interpolate to get the kernel of the workload to be simulated on our system, so that we be able to extrapolate the final performance result. So this is a very important way to build a methodology to get the summary of what's a typical workload you need to support, which is more complex for a general purpose processor chip, because that you need to suit for more different kind of workload, and find, as you say, that just a universal way to measure that in the runtime and also in the simulation time, design time. They are important that to cross-check between the different level to help you to correct your design. Then that's the biggest challenge we are facing today, I would say.
You mentioned performance, and for these large-scale computer, performance takes on a little bit different role. I mean, everybody always wants a high performance, right? No one's trying to build low performance devices. But the whole reason you're spending all the time and money and so forth to build these very large machines is for performance. That's the only reason you're doing it. So you know that you have to be able to measure the performance carefully and be able to say something as you extrapolate up from one processor to 10 to 100 to 1,000 and so on. Be able to say that the performance will, as you scale up, will meet your requirements along the way. So performance measurement is no longer an afterthought. Like, let's measure the performance and see if we get enough bytes going through from here to there. It's like you have to look at the whole thing all the way from the unit level on up and make sure that you're performing to your requirements.
So are you as well supportive of instrumentation to look at performance?
Yeah, right. There needs to be some hardware pieces in there so you can measure things along the way and be able to tell what's going on.
Okay.
To generate a little bit of controversy, I'm fully in favor of instrumentation, but depending on how you listen to the panel, you might think, well, we'll use that for Gen 2. That's way too late for many companies, definitely for startups. So yes, you want to put that instrumentation there because yes, that software at scale will need it, will use it, and you will learn a lot from it for your Gen 2, but you better do some performance extrapolation on a pre-silicon, right? Pre-silicon on your design to check that your basic variables are correct. And to this end, you were asking, what are you using? Someone has already mentioned the Barcelona Supercomputing Center. They have pretty good tools that can do multi-level simulation, fidelity simulation. So you may say, look, I'm in this OpenMP region of this very large application. I really don't care. I don't want you to simulate my CPU on an event basis and what happens every clock. Just believe me, in this region, IPC, instructions per cycle, is 0.3. Just do a quick calculation and move on with life. And then when you reach other regions, when you ask the simulator, please do me a high fidelity simulator, because simulation, I'm not sure what's going to happen here, or I want to explore this particular region more, right? And I think that should combine all the way down to the RTL, and should combine all the way down to emulation technology and be able to mix and match and say, I want now these million cycles to be run on my emulator, and I want to know how many, how long it took from this point in my program to this point in my program, and then let the other thing that's not logic emulation, that's just a software simulator, then keep going for a while and then maybe stop again and keep going. So that's how we plan to approach it. We're not there yet, but that's our plan to approach these very large scale simulations.
So I like Roger's word, mix and match. Very good word. And I think that's essentially what we have to do. I agree that for these large scale systems, you have to look at the very high level simulation where you make some abstractions on performance to be able to figure out where we're going, what direction we're going. But then there's the problem of being able to take that and bring it back down to the lower levels, to be able to tie it to your processor or your building blocks. And what I think we need there is to have a paradigm where we can move from the top level in kind of a mix and match simulation all the way down to emulation. And we successfully used something in Samsung when I was in Samsung. It was hybrid simulation with some of our mentors' tools, where we did things at the simulation level, at the functional level with IPCs, and then went to a performance model, which was more detailed at a very high level, and then went down all the way to a point where we're interested in, and then switch to an emulation environment for smaller building blocks, where we could have a seamless switch, an easy way to do that. And we found that to be very effective. In SiFive, we use something called FireSim that UC Berkeley created, which is similar to it's an FPGA emulation platform that uses Amazon Web Services, so it's scalable. And we have found that being able to do this mix and match and then switching over can be very helpful. We do that in Samsung. I think we need some kind of work like that. I know it's very difficult because workloads are huge. We don't even know what they are to go down to a deeper level, but there has to be some sort of flow to make that happen.
Okay.
I think that's fairly common. I mean, this is what, people in the System C world have been doing this kind of thing for a long time, where they mix abstraction levels from high level, very abstract models all the way down to RTL, where you work between Verilog and System Verilog and System C, and that's been very successful in lots of places.
But we need to put that into the emulation framework. Agreed with you there. Yeah. But it's much slower to go all the way to RTL. But if you can get the RTL in emulation and be able to switch from simulation to emulation, then we have a much better paradigm.
Yeah, I think that's quite doable.
Yeah, and there's, as Roger said, that there's no excuse not to do some correct architecture design from the top. As in, what in your system, what your throughput needs to be, what your computation is going to be, and you check those as you go down at various levels.
But you need to be, in the low level, you need to be as accurate as you can be. It's very good to have performance on the very high level and good models there. But we experience then when we do our interconnect, talking to different CPUs and GPUs, and then from different providers, that the models are not accurate enough. Yeah? That their internal architecture is not reflected enough to see what is the impact on communication between these CPUs. And then we want to scale them and put more and more together, and suddenly it doesn't work so well, because we designed it on some standards. We designed it on a PCIe standard, and this is a standard. But sometimes it's an impact of the internal architecture of the cache lines and how they handle credits and so on. So if the model of the CPUs we use at the end is not accurate enough, it will kill us when we try to scale it.
So the small building blocks have to be correct. Sorry, go ahead.
No, I mean, in this development detail, that will sometimes impact the actual system performance, because that there are some detail that decided your buffer size, your footprint of a program that always make system performance impacted.
Sir, you wanted to say something?
Yeah, I was listening to the speaker and I forgot what I was going to say. So it'll come back to me. It'll come back to me. Sorry, I forgot what I was going to say.
Okay, that's fine. Anybody else? Any other comment on that?
I remember now. So regarding the inaccuracies that was described, that Christian was mentioning, I believe that the small building blocks, you have to get that to be accurate. That has to be correct, because you're going to build on top of those and make assumptions and assertions on things, and the error can multiply, but you have to get the small building blocks correct. So I believe that the people who are doing the building blocks, they have to get their performance models very accurate. They have to get their functional models. They have to get the right pieces there, so that when things grow, however you abstract it, you don't add errors to it. Which brings me to a second piece that is related is, we're talking about performance, we talk about power, we talk about interconnections and all. However, there are new programming paradigms, and someone, I think it was Roger or Gajinder, mentioned programming paradigms that we're looking at, like, we're looking at vector, adding vector stuff. For SiFive, we're working to add vector instructions. But we don't really know all the applications that we're going to be doing at this Exascale effort. So what is the things we put into the architecture to be able to aid us in helping these new workloads? And that's another problem, another issue. But that is something that should also be looked at. So I think there's a sideways view you should also look at, is as you develop all this extra stuff for acceleration or whatever, what do you need to do to make sure it can scale up?
Anybody else want to add on what Nasr mentioned?
I'm tempted to say that, since the beginning of computing, every generation of hardware has built the next generation with the previous software, and that's always going to be the case. So
very true.
I've stopped worrying about it. You feel bad about it for many years in your career, and then one day you stop because, your goal is to provide more performance in the hand of those software developers, and they will invent something that you did not expect, period. So, it's fine to say that you do co-design, which is a good thing. It's fine to say that you're looking forward, but it's never really true. You don't know what the software community is going to invent. Nobody in this panel, I'm sorry for speaking for you, but I don't think we know what's going to happen in the next 4 years in software. And there are revolutions that just show up and take everyone off guard. And then, new hardware adapts. But, as long as you're focused, and Mark said it very well, nobody does this to be low performance. You always do it to do better than the previous one, more performance, less power. And as long as you do that, I think you're fine. Of course, you want to have an idea where you're going, but I don't obsess too much about not having the next workload, because you don't know what it is.
Roger brought up a good point, and I'll give you an example that illustrates Roger's point. We don't know what's going to happen. When I was working at Samsung, we spent a lot of time on getting good performance on our phones. And we ended up bringing the phones out, those prototypes out the year before Samsung released them. And we were finding out that our performance was very bad for some reason. For games, we were starting games up. We couldn't understand that, why it was. And so we're saying, look at the workload, look at the vector instructions, everything. What was the problem? And you know what we found the problem to be was, it was something in the Android system called the governor. And this governor raised the frequency of the part when you switch tasks. To save power, it would bring everything down to maybe 100 megahertz or so. And then when you switched, it would start ramping up. And the ramp rate of it going up to 2 gigahertz was what determined the performance. That, a lot of the big things were happening when it was still 200 megahertz or 300 megahertz. Something quite we didn't even think of. We were thinking about all these other things to optimize here and there. And it was something in the system code of switching.
But it's still part of the system. That needs to be considered as the whole, right? So it's not just your application. The whole system needs to be considered. So
including system software, which a lot of us.
Well, it's the system. It's part of the system.
Yes.
Right, but that's where there's a break, right? When the system, the SoC, the phone does feed in a emulation environment, and I think many people have done that. Even the GPU with its multi-FPGA simulations now, you can spend a lot of money and buy one of those emulation systems and actually see the full system in action. That's absolutely great. The problem is what happens when the system is beyond any vendors or even the union of all vendors. You bought all their production for the next year and the system is still outside the range of that. What do you do then, right? I think the question that our moderator was asking, and I think, at least to me, the answer is, multi-scale, multi-level fidelity is your only way out, because no matter how much money you have to buy emulators, you're not going to model the system. So you'll have to do in-system learning, and then pre-system, you have to do approximations at multi levels of fidelity.
Of course, if you're interested in buying a lot of emulators, we'll be very happy to talk to you offline.
If they're cheap.
Different question. All right, I think we are running out of time. This is the first time actually I'm moderating a Zoom virtual panel. So I hope it was efficient and effective for all of you guys and easy to do. It gives some challenges, but I think this is the way we have to do it nowadays. So I want to thank all of you guys for participating in many different regions around the world. And I think we're going to conclude, and everybody stay safe, and talk to you next time.
Thank you very much.
Everyone.
Thank you.
Thank you, Jean-Marie.
Bye-bye.
Thanks, everybody.
Bye.